In this session, we're going to dive into a very important component of Spark called Spark SQL. Despite Spark's rising popularity, SQL has been and still is the lingua franca for doing analytics. However, despite how widespread SQL is used, it's still a pain in the neck to connect big data processing pipelines like Spark or Hadoop to a SQL database. Usually for an application, one has to choose either SQL or something like Spark or Hadoop. Though wouldn't it be nice if it were possible to seamlessly intermix SQL queries with regular Scala code? And even better than that, wouldn't it be nice to get all of the optimizations that we're used to in the databases community on Spark jobs as well? So it's pretty common in databases to do all kinds of very advanced optimizations. But so far we have to optimize our compute pipelines in Spark by hand. Spark SQL is a component that delivers both of these two nice things. It makes it possible to seamlessly intermix SQL and Scala, and it also optimizes Spark SQL code very aggressively, kind of like using many of the same techniques from the databases world. So Spark SQL has three main goals. The first of which is to support relational processing in Spark. So this is that goal of intermixing relational code, declarative SQL-like syntax, with functional APIs like Spark's RDD API. And this is because it's sometimes more desirable to express a computation in SQL syntax than with a functional API and vice versa. So you could imagine that, for example, selecting an entire column out of a database is easier to do with a single line in a SQL statement than it is to do somehow with a map or a filter operation. And the other two main goals of Spark SQL is, of course, high performance, like previously mentioned, and support for getting data more easily into Spark. Wouldn't it be nice if we could just read in semi-structured data like JSON, for example? So Spark SQL seeks to add relational processing to Spark, bring super high performance from optimizations in the databases world, and to support reading in data from semi-structured and structured data sets. That said, what is Spark SQL? Is it like another system that we have to learn how to use? No, it's just a component of the Spark stack. So you can think of it as a library. It's a Spark module for structured data processing or sort of doing relational queries, and it's implemented as a library on top of Spark. So you can think of it as just adding new APIs to the APIs that you already know. You don't have to learn a new system or anything. And the three main APIs that it adds is SQL literal syntax and a thing called data frames and another thing called data sets. So these are the APIs, these are the things that you see and have access to. And on the back end, it adds two new back-end components. It adds something called Catalyst, which is a query optimizer. This is the component that will optimize your code. And another component called Tungsten, which is an off-heap serializer. Or said another way, it's a system that encodes Scala objects in a very, very efficient representation off-heap, away from the garbage collector. So these are the main things that Spark SQL adds: APIs and some stuff on the back end that should speed up your code quite a bit. Just to give you a visual depiction of how Spark relates to the rest of the whole Spark ecosystem. So we have this system called Spark, and inside of it we have this RDD API. We've been operating this entire course on these things called RDDs. We've been doing functional transformations on them. They're sort of the core data structure of Spark. Spark SQL sits on top of Spark as a library. It has its own APIs, and it has this thing called the Catalyst Optimizer, and while it has its own data frame API, it ultimately runs on RDDs under the covers. And on top of Spark SQL, you have everything else, like the console and regular user programs, so a user can write programs both using the data frame API and RDDs and freely intermix them. But the bottom line here is that we have this API that then does some optimizations and ultimately runs RDDs under the covers. So Spark SQL is a Spark component that provides a SQL-like API on top of Spark. This is neat because everything about SQL is structured. In fact, SQL stands for structural query language. It has a fixed set of data types, so things like longs, integers, strings, arrays even, and it has a fixed set of operations: select, where, group by, etc. And for decades, both research and industry surrounding these relational databases have focused on exploiting this rigidness, these known data types and these known operations to get all kinds of performance speedups. Since knowledge of SQL or databases wasn't a required prerequisite for this course, I'm just going to quickly spend a slide running through vocabulary. When thinking in SQL, data is organized into one or more tables. So here's an example of what a table might look like. There's a header. Tables have columns, which are named, for example, customer name or destination or ticket price, and then there are rows, so records. And a table typically represents some kind of collection or data set. So you might have a table and think of it as a table of customers. So we can think of this as the CFF or SBB customer data set. So like the train data set that we were looking at in an earlier session. This is how you think about a table. It's kind of like a collection of data. Other words that you might hear used, a relation is just a table, and attributes are columns. So this customer name here is an attribute. So this is just a column. Rows are also called either records or tuples. So this row here represents a record or a tuple. This record represents, for example, a ticket purchase. This is the last name of the customer, the destination of the customer, and the price that the customer paid for their ticket. This is one record in our data set representing that purchase. So this is the terminology that we're going to use. We have tables, also known as relations. We have columns in our tables, which are also known as attributes. And then we have rows, which are also known as records or tuples. Now back to Spark SQL. Spark SQL's core abstraction is known as a data frame. And every time we use the word data frame, you can imagine it as being conceptually equivalent to a table in a relational database. So data frames are conceptually distributed collections of records. And these records, they have a known schema. Okay? And super important is this point here, that unlike RDDs, which are also a kind of distributed collection, data frames require some kind of schema information about the data that it contains. Data frames are also untyped. Okay? This is an important point that's going to come back to. What do I mean by untyped? Well, I mean that it doesn't have some kind of type parameter that the Scala compiler statically checks. Compare that for a moment with RDDs. RDDs have a type parameter. So we can always make sure that the type that's inside of an RDD makes sense. However, data frames have no type parameter. They can contain rows, which can contain any schema, which the Scala compiler doesn't have a lot of ability to type check. And finally, one last terminological point, transformations. Transformations on data frames are called untyped transformations. This terminology is going to also come back to us later. Real quick before I go any further, we got to talk about the Spark session object. So if you remember the Spark context from the rest of this course, the Spark session is basically the Spark context for everything Spark SQL. So you're going to now have to switch to using this Spark session instead of Spark context. And to create and use one of these Spark session objects is still pretty straightforward. You just import the Spark session object, and there's this builder pattern here. You can add custom configurations that you'd like, but in general you have to start with a builder, you have to name your app, and then you have to say get or create. So you can have any number of configuration options in the middle here, but this is the general shape, and this is kind of the minimum that you need to start a new Spark session. Another important thing to note is the Spark session object, I believe, is meant to supersede Spark context down the line. So this is something that you should start looking into. So let's get into it. How do we create a data frame? There are two ways to create a data frame, either from an existing RDD or by reading in some kind of specific data source from files. So reading in some kind of common structured or semi-structured format like JSON. And for creating a data frame from an existing RDD, we can do it via two ways, either by inferring the schema or by explicitly providing the schema that should be contained inside of our data frame. So the first way to create a data frame that I'm going to cover is to create one from an existing RDD by reflectively inferring the schema, okay? This is probably the most convenient way to create data frames. So assuming that you have some kind of RDD, let's just say in this case it's a tuple RDD, to turn our tuple RDD into a data frame, all we have to do is call toDF on it. We can pass arguments to toDF, which represent the names of the columns. If we don't pass this list of column names to toDF when we call it, then Spark will assign numbers as attributes or column names to your data frame. They'll be usually something like this, _1 or _2 or _3 for the number of the column. However, if you have an RDD of case classes, things are even more convenient. So assuming we have this case class person and we have an RDD of person, all we have to do is call toDF on this RDD of person objects. And in this case, the column names automatically get inferred to be the names of the fields of this case class. And again, this is done all via reflection. The other way to create a data frame from an existing RDD, which is quite a bit involved, is to explicitly specify a schema. And this is useful for the case where you don't have some kind of predefined case class that you can use as its schema. Like I said, this is a bit involved, so bear with me here. It takes 3 steps. First, you create an RDD of rows from the original RDD. Then you create a schema separately that matches the structure of rows. Then, finally, you apply that schema to your RDD of rows using this method called createDataFrame. So let's step through a quick example, and like I said, this is a little bit involved, so please bear with me. For the sake of this example, I'm just going to stick with a case class, even though I know it's possible to use the 2DF method. Just stick with me here. So assuming I have an RDD full of these person objects, I first have to encode the schema in a string, so I have to do this manually. Then I have to build up a schema using these struct type things and struct field things that matches the shape of the data that I'm trying to build a schema for. So this is done by breaking up this string and then mapping on it and creating a struct field for each part of the schema, which has the name in the string here as the parameter. It has a type called string type, which we'll see later, and nullable is set to true. Like I said, we'll see some of these things later, and then all of that goes inside of something called struct type, and now we have a schema. So this is what a schema looks like. We build up a schema from these things called struct type, struct fields. Then we convert our RDD of people to a row RDD. Then we convert our people RDD into a row RDD by breaking it up and mapping everything to row objects. And finally, we can use this createDataFrame method on the Spark session object and pass to it the row RDD that we just created as well as the schema that we just created. So that's how you manually explicitly build up a schema and then create a data frame from that schema. It's a bit involved, but it's sometimes necessary. And finally, likely the most convenient way to create a data frame is by reading in data from a source file. So using the same Spark session object, you can read in a number of semi-structured or structured data types using the read method. So there's this read method on the Spark session object, and then you can read in, you can specify what you'd like to read in, for example, JSON, and then you specify a path to this JSON file. It's kind of like read text file, but it's better. It'll parse semi-structured and structured data, and it will build up a data frame with that schema of that semi-structured or structured data. And of course, it's important to note that there are a handful of formats that Spark SQL can just automatically read in for you. It can't read in arbitrarily anything, but the most common are probably going to be JSON, CSV, and Parquet. There are more methods available for directly reading in semi-structured and structured data. To see that entire list, you can visit the docs, which are here in the slides. Now that you know how to make data frames, once you have a data frame, you can freely write familiar SQL syntax to operate on your data frame. So how do we use plain old SQL syntax on a data frame? Assuming that we have a data frame called peopleDF, all we have to do is register our data frame as a temporary SQL view. So there's a method called create or replace temp view here that you can call on your data frame. This gives you a name that you can refer to in your SQL from statement. So in order to use SQL syntax, you need to register your data frame as a table, and then you can operate on it in regular SQL syntax. So now that I have this temporary SQL view registered called people, I can freely use it inside of a SQL query. So to do a SQL query in Spark, once you have a data frame, call the SQL method on the Spark session object and pass to it a SQL query, which refers to a registered temporary SQL view. So in this case, people. So in this query, we select all rows from this people table where the age field is greater than 17, for example. It's quite convenient, isn't it? Now, since you know you're writing SQL queries on top of Spark, which is not a SQL database, you might ask which SQL statements you have available to you. Well, the SQL statements that are available to you are largely what's available in the Hive query language. So this includes standard SQL statements such as select, from, where, count, having, group by, order by, sort by, and of course all of the joins. And also importantly, you can do subqueries as well in this syntax. Most everything from HiveQL is supported, so you can usually just try it out and see if it works. But if you want to collect more information about what syntax may or may not be supported, I've included a number of links for you here in the slides. There's a cheat sheet for HiveQL, a list of supported Spark SQL syntax, and an updated list of supported Hive features in Spark SQL on the Spark official documentation. So let's do a more interesting SQL query, because so far we've just created data frames and we've done a really simple query. Let's now assume we have a data frame representing a data set of employees. So how do we create that data set of employees? Well, we have a case class employee here with a number of fields: ID, which has type integer, first name, last name, both type string, age, type integer, and then the city that this person lives in, type string here. And to create a data frame, we simply create an RDD and then call 2df on it. So now we have a data frame full of these employee records here. Now it's time for a little quiz. Let's query this data set to obtain just the IDs and the last names of the employees working in a specific city. Let's say Sydney, Australia. And then, once we've obtained that, let's sort our result in order of increasing employee ID. So that means we want the IDs and last names column of this employee data frame for only employees that work in a specific city. And then after we're done with that, we want to sort our employees in order of increasing employee ID. So I leave it to you. How would you write this SQL query? Well, it's not too difficult. Let's assume that we have a table registered with the name employees. I left that out on the last slide, but assuming we have this table registered, all we have to do is say select ID and last name. So we select these two columns from this employees table, and we filter out everybody who lives in Sydney. And then we just order by the ID. To make sure we understand this query, let's visualize it. So assuming that this is our data set here, so we have this employee data frame. So assuming we have this data set here, this is our employee data frame. And remember, we register it as a table called employees. This is what the result of the query looks like. We've obtained our resulting dataset by selecting only these two columns, and then filtering out the records where city equals Sydney. So we get rid of these two people that live in New York here, and then we sort the elements by order of increasing ID numbers. So in this dataset, the IDs are backwards, and here they're now in the right order. So this is how So the bottom line, now we know how to create data frames and how to do arbitrary SQL queries on top of them. Pretty cool.